What I'm looking at today then is two things: to show that a mass on a spring is performing simple harmonic motion, and to find an expression for the period of oscillation. Now, you know this expression already, I think, but this will prove that expression to you. So I've got a spring here, which is unloaded, and I have a pointer here to show the position of the end of the spring. Here we have the spring with a mass on the end of the spring, and it's in equilibrium. So we've added the mass and we've allowed the system to come to equilibrium. In this third situation, what has happened is the mass has been displaced from equilibrium, so it's been pulled down or it's been pushed up and then released, and of course then the mass will oscillate. And this is a snapshot of that oscillation, where we are now X meters above the position that the mass was in here in 2. So let's consider the position situation in diagram 2. And let's work through the maths of this. The first thing we're doing, as I say, is to show that this is simple harmonic motion. So it's in equilibrium, which means equilibrium means no acceleration. If it's not accelerating, then there is no resultant force acting, and that we have from Newton's second law. So what are the forces acting here? Well, we have the force due to the spring, the tension in the spring, acting up, and we have the force, the weight of the mass, mg, acting down. So those two forces are equal. So we have Ke equals mg. Remember, Ke by Hooke's law, the extension of a spring is proportional to the force causing the extension, and the constant of proportionality is the spring constant K. All of that should be familiar to you. So we have an expression that K times E, the extension of the spring, equals mg. So let's move on then to look at situation 3, where the mass has been set in oscillation, it's been displaced from the equilibrium position, and at some point released then, and at some point in that oscillation we've taken this snapshot. So the force due to the spring now would be K times E minus X. And that gives us a resultant force of that minus mg. So the force due to the spring, K E minus X, and the resultant force, which is the overall force, is the force up due to the spring minus the force down due to the weight of the mass. So we can simplify that, or we can multiply out the brackets rather. So we have F equals Ke minus Kx minus mg. But of course, we know from our previous piece of work up here that Ke equals mg. So we can put that in there, Ke mg minus Kx minus mg. We have F equals minus Kx. Now this is beginning to look like simple harmonic motion, I think you'll agree. We have this minus sign in there. We have a proportionality to displacement. This is looking like simple harmonic motion, but we're not quite there yet. So that is our resultant force, and by Newton's second law then, our resultant force equals ma. So now we have A is minus kx over m. Sorry, minus k over m times x, is what I meant to say. So here we have the acceleration proportional to the displacement from the equilibrium position. You look up here. And always directed towards the equilibrium position. That is to say, when the acceleration is up, the displacement is down. When the acceleration is down, the displacement is up. So when the mass is up here, it's going up, slowing down, and so on. So we have A proportional to x, the displacement, and in the opposite direction, and that defines SHM. So we have demonstrated that a mass on a spring, when it's oscillating, is performing SHM. What about that expression that I said we were looking for? Now, since we know this is SHM, we can say the acceleration is minus omega squared x, which means, of course, that k over m is omega squared. And we also know from our earlier work on sorting out the equations for SHM that the period t, remember we were looking for an expression for the period, that the period is 2 pi over omega. So if we take our expression for omega, square root of k over m, put that in there, then we get t is 2 pi over m over k, which should be a familiar expression to you, but there it is. We have shown, firstly, that a mass in oscillation on the end of a spring performs SHM, and I have proven to you that this is the expression for the period of that oscillation. And you can see, as you might expect if you think about it, if you increase the mass on the end of the spring, you have a longer period, a lower frequency of oscillation. If you made your spring stiffer, so this was bigger, then this would be smaller and the period would be less.